Assalamualaikum warahmatullahi wabarakatuh and very good morning. Welcome back to Mechanism Design BMKU 4363. So in today's lecture, I'm gonna go through cams and chain design, and if we have the time, we're gonna start on statics, a little bit on statics. All right, let's get on to it. Let me share my screen. Hope we can see screen. So if you remember, we tried to solve the problem from the homework, a little bit from the homework. And if I can, let me try to pull up the homework 4. Maybe I can open from here. Let that open. It'll take some time. All right. Can I see enable editing here? And let's get to the part on cam design. So this is the motion sequence. So we have to rise using constant acceleration. So rise using constant acceleration. So let's get back to here. So in this new file, new tab that I created, we know that it is going to be constant acceleration for the first part. But so first type of motion, constant acceleration, and starts uh, from the beginning. So what you can do is can go to constant acceleration, which is parabolic, and under dr here, which is the delta r, the displacement, you go to the place where you know it is climbing or increasing or uh, rising. So this is the beginning of rising in this template for parabolic. So I'm gonna just copy that and go to our main tab. So you go to um, that cell for dr, and we know it's supposed to start from 0, time 0 or theta 0. And then you just paste it there. So then you must make some changes. Make some changes. So you know from mana soalan? From the question, you know the motion for that part or that regime is taking the time from 0 to 1.2. But if you know this parabolic, it uses you have to break it into two. So the rise part in the middle of it, you have to use another set of equation. So let's say this is from 0.5, the original, to 2.5. So this is the beginning part. This is the equation. But on the second half of it, the equation is a bit different. Okay. So I'm gonna copy, I can just copy this one, and that will be on the other half of it. So as you can see here, we were supposed to go from 0 to 1.2, but the middle class will be 0.6. So we double that. So the first 0.6 is for the first half of the rising of the rise. And the second part of the rise will be the second 0.6. So over here, let me paste the second part. Okay, just accept that for now. So let's see what we need to change. So this one will be the HO, which is supposed to start from the radius of the base, which is 1. So we start with there's a base circle. So that base circle has a radius of 1 inch. Okay, so you can set other value for that as well. But for now, for me, I set it at 1. So that is that. Then the rise, total rise is 2 inches. So 2 inches is from this cell. So that's G3. G3. So what else? We have to change this range from A5. Either you go with the time in A column or you go with the theta in the B column. So I think for the most part it'll be almost the same. But for now, let's go with the time. Or let's go with the time. So time will be A5 minus this one, change it to A5. So the initial or the first one will be 5. So this one will also be 5. And over here down in the 1.2 is 19. So this one, change it to 19. Okay, what else? I think that's about it. So that one will be 1. And you want to copy this all the way to the first 0.6. So you are supposed to get to from 1 up to 2. And then from here, you have a different set of range. Same range, but the overall equation is different. So this one will also go from, you change the one with the dollar sign. So this one will be, so this one goes by the apa nama, degrees, the angle, but actually can go either way. So I can also change this to A, change this to A, and this one is supposed to be 19. So we use time time just to be consistent. Okay, usually it's not going to be any problem, except in certain situation. So you see in the borders case, the value should also be the same. So if the one before the border is 2, the one after the border is also 2. But they are of different equation. So I'm gonna copy that up to the first 1.2. So you go all the way from 1 to 3. 1 to 2 and then 2 to 3. Okay, that's the rise part. And then after the rise will be a plateau from 1.2 to 1.5. So plateau, and then from the second 1.5 will be decrease using cycloidal regime. So you go to cycloidal and then copy the fall part. The fall part is, say, this one. So you just copy that, go back here, then from here 1.5, I'm just gonna paste it. Paste, okay. Don't worry about that change. It's supposed to be the same. If this is 3 before the border, after the border, supposed to be 3 also. But currently it's not. We'll see what to change. Okay, so this one, this one is supposed to be H of F, final. So where can I open the, yeah, so from here, supposed to go down from 3 to 2. So H of F here is 2. 2. So it doesn't go all the way back to 1. So it goes from 3 to 2. So our H of F is 2. H of F is 2. So how do I get back? So H of F is 2. So meaning in this equation, I'm gonna change this part to 2. And our delta H is just 1, not 2. So this is the original delta H if you go all the way up. But here when we fall, it doesn't go all the way by 2, but instead just by 1. So I'm gonna just change it directly over there. And here it's a bit jumbled up here. So here I think the other part uses the angle instead of time, but I'm just gonna change that back to time instead. So I hope you understand that the equation can both use both, usually by the same manner, by the same equation. So it's not a big difference. You can also jumble them up, except for a certain situation where you have to treat angles a little bit different from the time. Okay, so this is A24. So in this regime or this motion, supposed to go down up until 2.4. So you have to look back in the motion sequence. I guess is the next one is between 1.5 to 2.4. So that will be A24 to A33. So A24, A24. So this part is usually going to make it 0. So this part 66 to change to 33. This is 24. 24. This is 24. 33. 24. See how this will get you back to 3, which is the same across the border. So what you do is just copy that to the first 2.4. So here you see it's going back down or fall from 3 down to 2. Okay, so next to the border is a dwell. So dwell will be between 2.4 down to 3. So that is correct. And then after that, at 3, and the other 3 across the border until 3.9 is harmonic and also a fall. So fall, you have to go to this part. So fall is this one. So just copy that equation from harmonic scheme. Ini pun ada scheme. Don't be scheming. So from here, I want to paste that. Don't worry about that change. And you want to make the the outer. So this time 3 second to 3.9 is between 52 to 42. So I guess this one is going to be 0 lah. So we are interested until 3.9. So 3.0, the second one. So this one, the ES1 is going to be 2. This is going to back to, sorry, 1. E3 is 1. So I guess you can just put 1 there. And then this one, the total fall is also a 1. A 1. Okay, so that's a 1 and that's a 1. And the range is between 42 to 52. 42, so I'm going to change this to A. So if you go B, also that can work in most cases. So between that and here, change it to 42. 42, and this one change to 52. What else to change? Nothing else. So you see after the border, this one will be the same as this one, but the formula is different. So I'm just gonna copy that all the way to here. All the way to there. So it goes down to 1. So you start from 1, you go back to 1. So that completes the circle, the cycle. So for this one, I guess you can change the format. So it should be between, say, 0 to maybe 3.5. That will do. And this one between 0 and 3.9, or I'm just gonna go with 4. Okay. Yep. Okay, that's for the lovely cam displacement diagram. So then go ahead and save your work. But you can do pretty much the same thing, just copy from the right the correct column and do for velocity, acceleration, and then finally you can get your cam profile. So for the cam profile, it depends. If we see here, uh, you have to construct it using the PX and PY. So this one uses C5 is what? C5. Okay, this one. Or you can take the okay, yeah, this one. So it's gonna be different as you go on. So this DR is not going to be uh, it is crucial that we use the correct DR along the way. As we change the theta, we need to change the DR as well, the corresponding DR. And as you can see, with the correct timing here and the conversion factor between time and theta, we should get the theta going from 0 all the way to 360. So you have to ensure that you get that correct, as this is making one rotation. So this one will here we fix the column, so it's always going to be referring to column C, but the row is going to be changing as we go on. It'll be C6, C7, and so on. And this sine radian, so since sine, so Px will be the sine convention. Okay, so why we use sine, not cosine? So in this case, you can think about it, but it is using sine instead of cosine for x component. So, and then for y component, it's pretty much the same thing, but using cosine. We still refer to the C column, that is still the same. Okay, so this one will refer the angle. So but our angle here is in degrees. The trigonometric functions in Excel still uses radians, so you have to convert uh, the angles in degrees into radians like that. Okay, so that's how you get from the cam displacement diagram all the way to this one. So this one also you can change it to to get the better maybe the -5 to 5, and then do the same thing. Or maybe negative. Okay, let's go with that first. And then for this one, -5. So usually you want it to be a square thing, so that everything will be good. So I guess if we use 3 and 3, it will be much better lah. So it looks distorted, so got to have a square thing. So that's about it. Okay, and then so this one goes in this way. So it goes from here, from the middle here, in this direction, in the counterclockwise direction. So meaning This cam, when it operates, it'll go in the clockwise direction. So usually the way we construct it is opposite or opposed to the real rotation of the cam when it is operating in reality. Okay, so I have another file that I have already created everything, done everything last night. Tidak compat. So this one really takes some time, so but you have to do patiently do after doing the displacement, you do the velocity uh, copy from the right column or right cell, and then do the acceleration, and finally you can do you get pretty much the same thing, but you also have the information about the velocity and also the acceleration. Okay, so many great stuff there. So this motion jenis macam-macam lah. Is rojak. Maybe you can say rojak asembok. Got everything, a little bit of everything in the same. Not sure about reality. Rojak asembok. Anybody from Penang here? Okay. Yeah. That's about it in terms of this thing. But if you want to try to do it using MATLAB, you can pretty much copy paste from this one. But this one only gives you the apa nama, this one the profile, cam profile. Uh, Cam profile and cam displacement diagram. So this one is operating if you go by angle, and this one is operating if you go by time. So it doesn't matter. It'll look the same. It's supposed to look the same. That's why if you look in the scheme set of equation, they pretty much look the same. Either you go by time or you go by angle, except for a few instances where you need to time some modification factors or something like that. Okay, do you have any question? You can ask me later or message me, send me a text. Okay, if you don't have any question, let's get on to uh, the other day we already started on on belt and chain. Let's see if I can open that up. Okay, let's backtrack a little bit because I remember Monday I said we don't want to focus too much on the health part because you have already learned that. But pretty much belt and chains what we call flexible mechanism for power transmission. So they are uh, all around us in our daily household products. And if we look into it, you can see a lot of them in action. All right, so basically it can transmit rotary motion. So rotary motion. So meaning you can couple it pretty much with motor, whatever rotation, rotary motors. And then from there, with different sprockets or wheels or pulleys, we can vary the torque. We can change the torque. So usually you want to increase the torque from something that is fast and low torque to something that is a bit slower and higher torque. So, but all in all, it's called power transmission. So basically, you want to maintain the power, or as much as possible, you want to maintain the same power from the input to output. Okay, so what is interesting about this one compared to rigid body gears is that this one doesn't change the direction. So if our input is going clockwise, so the output will also going clockwise. So same direction. If you put it in this open configuration. So if you want it to be opposite, you have to cross configuration. Okay. And for most cases, if your input and output is a bit far apart, so using gear is definitely out of the question. Using gear will be uh, impractical to use gears, even though gears have higher efficiency, but because of the distance, why do you put them far apart? Okay, I remember when I was working, when I was studying, sometimes I have to go upstairs in the office in the top floor, and I had to go through the room where they put the motor for or the power thing for the elevator lift, our lift system. So we see some of the, I'm not sure what part of the machine, but the motor is a bit farther from the output, from the thing that it wants to power. So in that situation, I can see the belt being used to transmit the power from the motor to the the thing that you want to turn. So maybe there's some reason why we do not put the motor directly to the place. Maybe it's heavy, and if you put it but directly to the place or the part that you want to turn, maybe it's not going to be safe or something like that. Okay, so and then speaking about safety, this one has as a good thing about if the something happens like the motor spin a bit faster than usual, there's a power spike or something like that. So because this thing is flexible, so it can slip, which is not desirable, but things can happen. But when it slips, in that particular situation, maybe it's for a good reason. It doesn't damage the other part, the other perhaps more expensive part that you want to protect. Okay, so that's the situation. So as in chain, belt also and also gears, we can change the speed because of the difference in the pulley sizes. We can change the torque and the velocity. So in this case, angular velocity lah. So if the small one here is going by omega 1, so the big one will go a bit slower with omega 2. But whichever case, if you calculate the VB, the linear velocity, they should be the same. If this thing is considered, if the belt is considered or behaving as a rigid body, to transmit. So usually in belt and also in chain, but especially in belt, there's two part of the part here. One will be the tight part, one will be the slack part. So which one is going to be slack? Okay, you have to identify which one of the pulleys is the power, the input power. So if the input is from pulley number one, so we look into which part is being pulled. So in this case, the top part is being pulled by this rotation. So meaning this part is going to be the tight part. And this one is being pushed. So something that is flexible when it's being pushed is going to slack. So this lower part is going to be slack. Okay, so it depends on which part is supplying the power. And the ratio is like this. Usually we start with the angular velocity. Angular velocity. Then from there you can identify the equivalent ratio if you are using the size. In this case, the diameter. You can go with diameter or with the radius, things like that. So in this pulley usually do not have gear teeth, except for certain situation. We have a tooth pulley, like a cork type of belt. But other than that, most pulleys and sheath do not have teeth. All right. So we have flat belt, and this rotation part is called the pulley. And for V belt, this is also a pulley, but for V belt, they have a special name. They call it sheath. So when they say sheath, meaning that we are using V belts instead of a flat belt or round belt. And for timing belt, we have teeth like this. So a lot of more precise motion. We need to have this one timing belt. So in like for car engine, usually we can have this kind of belt being used. Okay, and then just like in chain, we have the linear velocity, VB, B for belt. So for chain, VC, C for chain. But they both go with FPM lah for US customary unit, or when we are dealing with inches. For metric, I guess we can go with meter per second. Meter per second. So how do we know we can use belt? So usually the range for ballpark range or ballpark value for VB is between 1000 FPM to 6500 FPM. So if you have to decide, maybe you take VB somewhere in between, like 2000, 3000, 4000. Okay, so if you have to decide VB, so from there, maybe if you have decided what VB is, you can find what the diameter or RPM. So by knowing these two things, you can find the other one that is unknown. So for this example, we have a motor, the input against a smaller pulley running at 1750 RPM clockwise. And then So the input shift, so it says shift meaning we are dealing with a V belt. So the input has a 4.5 inch, 4.5 shift. So that's the diameter of the shift attached to the motor, and drive 8-inch shift on the lathe. This will be the output. Determine the velocity of the driven shaft of the lathe and the belt speed. So I think that should be very easy to do lah. So we basically want to find omega 2 over here. So our input is 1750 and omega 2 is found to be, what is that, 984. So about 984.375 RPM. So it should be reducing from 1750 to 984. Okay, so it goes down. And then, so this is power transmission thing. V-belts, there are many brands or models out there, and it also depends on different manufacturer, and they might have different models available. But usually the 3V, 5V, and 8V are very much common, and they pretty much have this kind of sizes. So say if you want to transmit 10 horsepower, this one per belt. So if you want to have more and you have the same constraint, you can have a multi-strand belt. Multi-strand belt. I guess there's a picture here. So this one has two strand. Two strand. So, but a lot of other stuff you just use single strand. Single strand. Strand is spelled S-T-R-A-N-D. Strand. Okay, for the faster shaft, which is the input, so 1750 is this one. And this question doesn't mention the the horsepower you want to transmit. So just say you want to transmit 10 horsepower at 1750. So you are actually in this region, in the 3V region. So this is the kind of belt cross section that you can use. So this is also a multi-strand. We have three similar type of belt being used together in the same center distance and whatnot. So this is a flat belt. This is a serpentine. This is a cross drive. So cross drive will change the direction opposite. So input is clockwise, and this one output goes counterclockwise. But and this is open configuration. So usually if this one goes counterclockwise, this one goes the same direction. All right. And then once you have determined what type or model of belt that you want to use, in our previous case is a 3V. So meaning the sheath and also the belt that you have to select is going to be from that category. From that category. So belt, you just look into the 3V belt. Same as the sheath, you only look in the 3V category. Okay, so selecting is done by a few SOP or procedures. Okay, so these are what is available uh, off the shelf. Okay, and depends on the manufacturer. So then what you want to also look at is the number of length, belt length, you can calculate if you have decided what your center distance between the two pulleys or shifts. So you can find that. If this information is not given, so you can try to get somewhere in between. So C is supposed to be between D2. This is D2, D1, and 3 D2 plus D1. Okay, so usually you want to take somewhere in between, but sometimes that value is already decided or given to you, and you need to operate within that given value. So once you know what C is, and you know what D1, D2, you can pretty much calculate the belt length. Um, so once you got the belt length, you can go back to here, see if that that length is available. Okay, because they come in this kind of thing. Sometimes it's already stitched together. It's not from one big roll. So say you have a loop of belt that you can choose from. So you have to choose from what is available. So if not available, so you go to the closest one. So you either go one up or one down. Okay. So once you make your selection, you go back here and try to calculate whether you got the acceptable center distance here. Okay, usually for this kind of system, one of the pulley can slide. So you can make some little changes lah. Maybe make it a little bit to the left or a little bit to the right to adjust because you want it to be as tight as possible. You don't want it to be slack too much. Okay, so once you already know what your belt length is, so once you select the real belt length that is available, you can calculate this B value and then plug it into this one, and you can find the center distance, the realized center distance. Okay, this is something that you can calculate, contact angle. So usually it will be the same, the different for contact angle in the gear number 1 and contact angle gear number 2. Okay, so it has some implication in terms of how much power that you actually can deliver. Okay, so you can go through this example. I guess it's very straightforward. Okay, and yeah, let's move on to this chain thing. And so the chain, you need to also know the velocity ratio, and this is something that you can calculate the VC, and this is VC in FPM, and usually you want to limit it to 2500 FPM. Okay, so there'll be some ranges that you can either choose to work with chain or to use belt. Okay, like I mentioned, the class, the base one is this pitch, the chain number 80, because chain number 80 will result in a pitch of 1 inch. So 80 divided by 80 is 1. but you have other chain numbers as well. And all this also depends on the chain manufacturer. Okay, so here we have plenty of chain numbers to choose from, and from this where we have the arm on the bottom and also the power on the y-axis, and this depends on whether you have 1, 2, 3, or 4 strands. Okay, so you can put them in parallel. This is why do we do that? In terms of kinematics, they don't do much, but in terms of power transmission and also for load distribution, so that can maybe release the stress, reduce the stress on each chain strand, and that will increase the operational lifespan of the system. All right, so yeah, so once you have decided what chain size or chain number you want to work with, you have to follow that category. You have to follow that category. And in this case, from this table, you can find the number of teeth for the sprocket. So you have to choose at least 2 sprocket, one for the input and one for the output. Okay. Okay, so I guess in the lower part, it will have up by 1. So like here number 25, so it will have 8, 9, 10, all the way to through 30. And then you have 32, 34. So these are the available number of teeth uh, on the sprocket for that category, chain number 25. So if you go chain number 40, it'll be different. So you get up by 1 from 8 through 60, and then you jump to 64, 65, jump to 68, 70, and so on. Okay, this is also another important part. Since you choose by the number of teeth, but you also need to know what is the pitch diameter. So that one you can convert it from here. So put in the number here, say 80 teeth. So you say the pitch is 1 inch. So you can pretty much get what is the diameter there in terms of inches. So let me try that. So like 80 here. If I use this number, chain number 80, so that means the pitch is 1 inch, and then number teeth 80. So if I go to this equation, P is 1. P is 1 divided by a sine of 180 degrees divided by 80. So meaning my diameter here is about 25.47 or about 25.5 inches. 25. Pretty big size there. Okay. Again, we can, if we are given or we already know what C is, which is center to center distance. Yeah, this one. And once you, or if you are not given that information, you can try to get the C from this ballpark value, 30p to 50p. Okay, so this is the nice spot. Maybe take somewhere in between or in the middle. And if once you know C, you can calculate the number of L here, a link. So this is number of link, it's not length, number of links. So if each of this part is one link, this is one link. So you put many links just and form the chain. So in this situation, in this example, what is the question? I guess from example number one, huh? So this you you can calculate the pitch is 0.5, and you can get the velocity ratio, in this case 3.33. And once you know you can go through apa nama, the category 40, chain number 40, and find what are the two sprocket teeth that can get you close to 3.33. Okay, so you can if you decide N1 to be 25, so N2 should be 84, huh? 84. So if that is available, so you can choose one is 25 and the other one is 84. So gear teeth need to be integer lah, cannot be 83.25. Must must round it up to round it down. Okay, and then once you know that, and you have to decide what your C is, then you can calculate the number of links. Number of links. So here you can also calculate VC. VC. All right, uh, however, we only have 137. So here we calculated the number of links is 136. So that is 137 lah. 137. And then we can plug in the value here. Maybe put 137. So 137, let me check that. Do we have 137? Check from where? One 37. Actually, the highest that we have is 120. 120. 120 is the number of teeth. So let me check. Number of teeth is 120. Okay, we don't go that far up. We only use 84 and 25. Okay, so 84 and 25. 84 there, and 25 I believe is somewhere in this range. Okay, so that is available. Those are available, and we can plug in those numbers. 137 here. This is 0.5, and we should get our C is 20.07, which is exactly what we wanted, desired. Okay, and then there's another example here, and I guess you try to go through that example, and I think you should be good. You should be good. And I guess that's about it from this recording. And I wish you all the best. Assalamualaikum. Have a good one. Bye bye.